In the last section, we looked at linear equations in two variables and in their graph, like what they look like visually. And in this section, we're going to look at a system of linear equations in two variables, which is just two of these equations together. And we write a system like this in standard form. It's written this way with your x's and y's on one side and then the constants alone on the other side of the equation. And if we're solving a system of equations, we're just looking for the point, the x and y values that make both equations true at the same time. And just a quick word before we keep going, it's really common in a lot of books and writers that instead of using x and y, they might use different subscripts, so like x1 and x2 for the variables. I'm going to stick mostly with using x and y because we are just sticking to the two-dimensional graphs that we can, lines that we can graph on the xy coordinate axes. But if you look at other sources, don't be surprised if you see them, the writer using subscripts instead. So when we look for a solution, we're looking for the pair of values, one x and one y, that makes both equations true at the same time. Now, we're going to spend a bunch of time looking at how we precisely find this solution algebraically. But first, we're just going to learn what it means sort of visually, graphically, when we find a solution. So here's a system of equations. It is in standard form. And now I'm just going to begin by graphing both the lines. So I'm going to number these. So we've got line 1 and line 2. For line 1, and I'll graph them, I think, just by finding the axes, or the intercepts. That seems easiest. So for the x-intercept, I'm going to set y equal to 0. I'll start with line 1. And if I set y equal to 0, I get the equation 2x equals 8, and that means that x is equal to 4, and so it has an x-intercept of 4, 0. And for the y-intercept, we'll set x equal to 0, and if we set x equal to 0, that gives us y equals 8, which means it has the intercept 0, 8. Now, before I graph that line, I'm actually just going to go ahead and find the axes, the intercepts for the second line. I just want to get a sense of how far out I need to go on my axes before I start drawing out my tick marks and figure out what scale to use. So, line 2 for the x-intercept, I'll set y equal to 0. And if I set y equal to 0, that gives us the equation x equals 9, and so 9, 0 is the x-intercept. And for the y-intercept, we'll set x equal to 0. And if we set x equal to 0 in the second equation, we get the equation 3y equals 9, and dividing both sides by 3 gives us y equals 3. And so that gives us the y-intercept 0, 3. Alright, so now that I have both pairs of intercepts, we will sketch. I need to go out as far as 9 on the x-axis, and I need to go as far up as 8 on the y-axis, just looking at all of my intercepts. So there's 9, there's 4, there's 8, there's 3. And so let's see, and line 1 has an x-intercept of 4 and a y-intercept of 8. So there's the first line. And line 2 has a x-intercept of 9 and a y-intercept of 3. So keep in mind, so that's line 2, when we graph a line, when we graph the equation of a line, what we are seeing is all xy pairs that make that equation true. So all xy pairs that make the first equation true are on this line here, right, that's labeled as line 1. And all the xy pairs that make the second equation true are on this other line here, labeled as line number 2. And if what I'm looking for is the set of values, one for x and one for y, that makes both equations true at the same time, that means I'm looking to see if these lines cross. They do. They cross right here. So that's the solution. I can tell that there's only one place where they cross, right? Looking at the trajectory of these lines, these lines aren't gonna turn around, right, and cross again. There's only one point where they cross. It looks like they cross at the point maybe 3, 2. So it looks like x equals 3, y equals 2 is a pretty good guess about where these two lines cross. But again, we'll just note that that's sort of the best we can do when we solve them graphically. It's just sort of, it looks like this is where the solution is. It is not a very precise way to find the solution, but it is a really illuminating way to think about what we're looking for. And before we spend time on finding these solutions algebraically, we're just going to look at what's possible when we think about these visually, what types of solutions we might get. So the solution in the last example that we saw, we could see that they're only going to cross once. So there's one point, and we say that that system has a unique solution, and that's always true in systems like that one. And here's another one in part A. These two lines have different slopes, right? So there's going to be one point where they cross. It's also possible to get a system with no solution. That happens if your two lines are parallel, but not equal to each other. So that's what we see happening in the middle graph here. And then it's also possible that the two lines just coincide. And when you graph them, they're in fact one line is just on top of the other. They are the same line. In that case, there's infinitely many solutions. And we'll see kind of how to recognize these systems, these different types of solutions algebraically. So there's two techniques that we're going to learn. One is the method of substitution, and in that scenario, in that method, we're going to pick one equation, solve it for one of the variables. It doesn't matter which equation or which variable, so usually we pick whichever seems kind of like an easy option. And then once you have that expression, you plug that expression into the other equation. You have to make sure that you use the other equation, otherwise all your variables will disappear, and something kind of weird will happen. So you plug it into the other equation, and you'll get an equation with just one variable that we know how to solve. We know how to solve those types of linear equations. And once you know the value of one of your variables, then you can use one equation, another equation to solve for the other variable. So that's sort of like pretty wordy. I'm just going to show you what I mean in this example. So here's that system that we graphed near the beginning, right, a couple pages ago. Now we're going to solve it algebraically. So I want to pick one of these equations and solve it for one of the variables. So just looking at what we've got here, I'm either going to pick equation 1 and solve it for y, or equation 2 and solve it for x, just because that seems easiest. I won't end up with any fractions that I have to work with. So I think what I'll do here is I'll just solve equation 1 for y. So 2x plus y equals 8. If I subtract 2x from both sides, I get y equals negative 2x plus 8. If you wrote 8 minus 2x, that's perfectly fine. They're equivalent. So there's my expression for y in terms of x. Now I'm going to plug this in to the other equation. So I used equation 1 to get that expression for y. So I'm going to plug it into equation 2. So this equation is x plus 3y equals 9. So I'm going to take this and plug it in for y right there. And this is an equation. It's a linear equation in one variable. We know how to solve those. So I'm going to distribute that 3. Combine like terms, and also, all of my x's are already on the left, so I'm going to go ahead and get my constants on the right. I'm going to subtract 24 from both sides. X minus 6x is a negative 5x. 9 minus 24 is negative 15. And then we divide by negative 5. And negative 15 over negative 5 is a positive 3. Now that I know the value of x, there's my x coordinate, I'm going to find y. Now I could find y using either of the two original equations up here, or I could say up here, and then my first step, I already solved for y in terms of x. So I think I'm going to use that to find y. So negative 2 times 3 plus 8, negative 6 plus 8, or 2. And now the solution to a system of equations is a pair of values. I don't want to present it as two different solutions. So I'm going to either express it as the pair x equals 3, y equals 2 together. You could also give it as a point, 3, 2. Just make sure that x goes first. If you write it as a point, you've got to put the x coordinate first. So this is how we solve a system using the method of substitution. The other algebraic technique is called elimination by addition. Here you have to make sure in the beginning that both of your equations are written in standard form. That's pretty important because you want those variables to kind of line up nicely on top of each other. When you solve by elimination by addition, the idea is that we're going to add the equations together and one of the variables will just disappear. And in order for that to happen, you want to make sure that the coefficients on that variable are equal but opposite, like the plus 5 and minus 5, or plus 2/3 and minus 2/3, or something like that. And so in order to accomplish that, we're going to multiply both sides of one equation by a constant, so that when I add them together, that variable will be eliminated. Or sometimes you might need to multiply each equation by its own constant, depending on what those coefficients look like. So we just sort of determine what is that least common multiple. And then we add the equations together. So I'm going to stop talking about this and start showing, demonstrating in this next example. So when you solve using elimination by addition, you want to first, pick a variable to eliminate. It'll always work, regardless of which variable you pick, it will work each time. Sometimes one choice might be easier than the other. So in this example, it'll actually be easiest to pick x because I can do that and only have to multiply the top equation by a number, and I don't have to multiply the bottom equation by anything. So if I take this top equation and I say let's multiply it by negative 2, the bottom equation I'm going to make no change. Multiplying the top equation by negative 2, everything gets zapped with a negative 2, so we have negative 2x plus 10y equals negative 8. The bottom equation we're not making any changes, so we have positive 2x plus 3y equals negative 5. Now I'm going to add these equations together. Look what happens to the x's. I have a minus 2x plus 2x. Those cancel each other out. That's just a 0. So now this becomes just, 13y equals negative 13. And we solve by dividing by both sides by 13, and we get negative 1. Once you have one value, then you can just find the value of your other variable by plugging it into one of your equations. So you don't have to use elimination again. You can use elimination by addition both times, but it's always true that if once you have one of your variables, the values of one variable, you can just plug it in to get the other one. So let's say I'll take that top equation just because it seems easiest, and I'm going to plug that in. So that's x plus 5 equals 4, and if we subtract 5 from both sides, we get -1 again. So the solution to the system is x equals -1, y equals -1. Okay, let's try another one. We're going to use elimination by addition. In this case, what made the last one kind of simple and it was clear that we had to pick x was just that I only had to multiply one equation by a number, to get these coefficients to be equal but opposite, because the coefficient of x in the second equation was just a multiple of the coefficient of x in the top. Down here, that's not quite the case, unless I want to use fractions, and I love fractions, but it's kind of easier to kind of try to avoid fractions and stick with the whole numbers. So in order to eliminate a variable, I'm going to just pick a variable, and then I'm going to have to multiply both equations by some number, each equation by its own value, to eliminate a variable. So let's say I pick to eliminate y. All right, so I'm going to eliminate y. I'm going to see that my coefficients here are -2 and +3, and the least common multiple of 2 and 3 is 6. So I'm going to multiply each equation by a number to get those coefficients to be 6, and I want to make sure they're different signs. Now these are already different signs. That's good for us. That means I'm just going to multiply both top equation and bottom equation by a positive. I'll multiply the top equation by +3. I'll multiply the bottom equation by +2. Now on the top, when I multiply through by 3, I get 15x minus 6y equals 36. On the bottom, multiplying through by 2, I get 4x plus 6y equals 2. Now when I add these together, I could see that the y's will cancel. I got -6y plus 6y, so that goes to 0. And I'm left with, on the left side, 15x plus 4x is 19x equals 38. Dividing both sides by 19 gives us 2. And now I can use this known value of x and use one of the equations to solve for y. So maybe I'll pick the second equation. So 2x plus 3y equals 1. I'm going to take my known value of x and plug it in there. So I have 4 plus 3y equals 1. We'll subtract 4 from both sides. That gives us 3y equals -3. And dividing both sides by 3 gives us y equals -1. So my solution to the system is the pair of values, x equals 2, y equals -1. All right, so let's do a couple more examples here. We can, we mentioned in the beginning, near the beginning, that depending on how the lines look, I'm just going to scroll back up here, that we might be in a situation where there's just one solution. Maybe there could be no solution though, or maybe there's infinitely many. The examples we've done so far have all been like this first one, where there's just a unique solution. I got two lines that cross at one point. Our algebraic techniques can also tell us when there's no solution or when there are infinitely many solutions. So let's say we're going through and solving this equation, or this system rather, and we pick a technique to use. So, let's say I'm a fan of elimination by addition, so I'm just going to use elimination by addition to solve this system. And I'm going to make no change up top, because I'm going to eliminate the x's, I guess. I'm going to make no change up top. I'm going to multiply the bottom by -2. And this gives us, so the top equation is the same, 2x plus 6y equals -3. And now on the bottom, when I multiply through by -2, I get -2x minus 6y equals -4. Now look what happens when we add these together. The 2x's, as planned, go to 0, but look, the same thing happens to the y's. So I've lost all of my variables. Something weird is happening. On the left side, I just have 0. On the right side, I have -7. So when you lose all of your variables, when you're solving, using either elimination by addition or substitution, and you find that all of your variables disappear, you're in one of these scenarios where there's either no solution or infinitely many. And to determine what situation it is, you just look at the equation. This, the equation that we got when we eliminate these variables, this is never true. Right? There's no values of x and y that you're going to find that's going to somehow make 0 equal to -7. And so what that means is that this system of equations has no solution. If you graphed these lines, they would be parallel, but not the same. So you'd see two different lines that are parallel to each other. You could see that they never cross. And if you find their two slopes, you'll see that they have the same slope and different y intercepts. Let's try another one. Let's say we want to solve this system of equations. Again, I'm going to go ahead and multiply. I'm going to use elimination by addition. So if I wanted to say eliminate the x's, I'm going to multiply that top equation by +3, and I'm going to not change the bottom one at all. So multiplying the top equation by 3, +3 gives us 3x minus y equals -6. On the bottom, we get, there's no change, so that's -3x plus y equals 6. Now when I add these together, again, we see something weird happening, right? The x's are eliminated as planned. That was our plan. But look, the y's are eliminated as well. And so, again, on the left side, we have 0. We've lost all of our variables, so we know something weird is happening. On the right side, -6 plus 6 is 0. So this time, the equation that resulted when I lost all my variables is something that is true all the time, right? So this is always true. No matter what value of x you might find, right? 0 is always equal to 0. And that means that there are infinitely many solutions. So this is a scenario where if I graphed the two lines, they'd actually be the same line. They'd have the same slope and same y-intercept. Now, infinitely many solutions doesn't mean that every xy pair is a solution, but it means that every xy pair that satisfies one equation will also satisfy the other one. So then that gives us infinitely many pairs.